Our next speaker is Professor Raoul Bott, who is Professor Emeritus in the Mathematics Department at Harvard University. Raoul, it's a pleasure to welcome you. Well, it's quite a crowd here. It's a great honor to be brought here all the way from California on this very nice occasion. I came here, of course, 56 years ago, and to a large extent, I think my benefactor who brought me here was Hermann Weyl. George Dyson yesterday informed me that he found the paper where they were selecting the people for admission that year. And he found my name on the list of doubtful candidates. So I was a candidate that had not been informed that they had been accepted, but they had not been informed that they had not been accepted. Yeah. So I decided that, as usual, between my two friends, that I'm talking that I'll be on the lighter side of this subject. And after the imposing stuff Mike was told, I think you'll find my talk much easier to understand. And coming back to Hermann Weyl again, he liked to sit with us young people up in the little restaurant, and then he would often say, "Oh, you poor people, mathematics has become so complicated." Especially, I remember he once mentioned Fritz Hirzebruch's Riemann-Roch theorem, which he thought was unbelievably complicated compared to the mathematics that he himself had done in his life. And he would give examples. And so the title of my talk is really what Marston Morse missed by not talking to Hermann Weyl, in a sense. And it was my good fortune to sort of to pick up on there. So I came here as an engineer, and topology was a pretty difficult subject to understand. But questions of this sort I was able to understand. So according to Morse, if you had a function on a manifold, you should look at its critical points and count the critical points by how many directions of steepest descent came from it. Now, even as an engineer, I knew what that was. So, for instance, I learned the following picture. Here is the two-sphere. You take a point outside and look at the distance function. Then, of course, it's easy to see that the critical points correspond to the places where the straight lines meet the thing at right angles. And so the two critical points are here and here. Here is the minimum, and here is the maximum. And here is a wonderful point, the center of the circle. You notice that these 2 points are the symmetry, one takes into the other. And this is the minimum, this is the maximum. And this is what in geometry is called the focal point of this shape along this line. And it's of course means because all these normals come together here. And so in the Morse counting of this function, you would write down a 1 for this, and a t squared for this, because there are two directions of steepest descent, independent directions, and this would then be the Morse counting function of this function. And the nice, and to me I immediately loved this theorem, that his theorem was really that if you do this in general on a manifold, this function of course depends on the original function, the counting function, but it satisfies certain inequalities. But more than that, if you are lucky, then the inequalities become equalities. And in particular, for instance, if all the exponents that you find are even, then automatically this function is a perfect, as we call it, perfect Morse function. Well, this is what I would sort of call the baby, what we used to call the baby Morse theory. What really fascinated me was that he had, and that was of course also to a large extent his fame rested on this theorem, that for instance he proved that there are an infinite number of geodesics joining any 2 points on a sphere. And he used the Morse theory there in the following way. So the problem was, so the theorem is that you can do the same sort of thing if you study the function on the loop space of a manifold. That means you take a manifold M and you study all the paths that join a point P to Q. You take the energy along that path, and the extreme of that are the geodesics. And you can count the geodesics by their critical points. And they turn out to have the marvelous property that the number of negative directions is always finite. And so you can formally write down the same sort of series. So let's, for instance, do that for the two-sphere. Again. So we start here, and we choose a nearby point Q, and we start to study the critical points of this situation. Well, you see, the geodesic segment, here is, of course, a geodesic, but that's not all. You can also go this way. You can, of course, also go this way, and so on. So you see that there's an infinite number of critical points immediately. And you can write down the Morse series very easily, because it turns out that what is the focal point there in this situation becomes a conjugate point, and the conjugate points are precisely, the conjugate points of P is precisely the antipode and P itself. And so instead of looking, Morse's very beautiful so-called index theorem said that to count the number of negative directions, you just have to count the number of conjugate points along each geodesic. So for instance, if we do this, you will see on the two-sphere, you will see that this thing here counts for 1. This fellow here, I don't see quite from, yeah, this fellow here crosses the conjugate point once, so it adds a t, and then you'll find one that they add one more each time we go around, so you get this series. Now this series, actually, the way it stands, would only satisfy inequalities. Actually, if I write it, it's 1 over 1 minus t. It's a shorter way of writing it. So here we don't know whether this is really describes a Poincare polynomial of the loop space. But actually, one could show that it does. But certainly, if I'd switched to a higher sphere, if I'd switched, let's say, to the 3 sphere, then it's fairly easy to see that these multiplicities change. And so then you would have had, for the 3 sphere, the corresponding 1 over 1 minus t squared. This would be the answer. And this would prove that the cohomology of the space of loops on a sphere has this Poincare series. So I think that was a wonderful result, and it's interesting that when I was here in Princeton, the topologists paid no attention to this, really. You know, I mean, and never did I hear on Fine Hall anybody comment on this fact. It was just completely ignored. And this was, of course, in 49. Then, of course, Serre appeared in 51 or so, and suddenly loop spaces and so on became the bread and butter of all of us topologists, but in a quite different way, not in the Morse way. And before Serre, nobody thought it was interesting that one could compute the cohomology of such interesting function spaces by such easy geometric computations. All except me, I must say. I enjoyed this very much. So, is there an eraser here? Can I erase? I guess not. A bit terrifying. So, oh, thanks. So when I left the institute, went to Michigan, and there I started to learn about Lie groups. And as Michael was saying, one loves one's first theorem, so that's the one I'm going to talk about, which I discovered there in about 52 or so. So as I learned about Lie groups, of course, I came to appreciate this picture of the two-sphere in a different way. The two-sphere is the adjoint orbit of the SO3 group of symmetries. And so when I went home, and as I say, in Michigan, I started to think about the next group, so to speak, SU3, which is a three-sphere. And then I saw right away that we had already computed the Poincare series of the three-sphere. So we were on the way. So, sorry, SU2. SU2 really, Morse's way of computing gave the cohomology of the loop space of the three-sphere. And so the next step was to look at SU3. And now, the marvelous thing is that you see in the orbit of SU2, the two-sphere intersects this line in just these points. Well, there's a corresponding phenomenon in all Lie groups, has to do with the Cartan subalgebra, but in this example, it has to do with that you have a two-dimensional plane, and if you take the orbit of anything in the adjoint representation, it will intersect that two plane in a similar way in which this orbit intersected that line. And in fact, what you find then is that if you take the matrices then, 3 by 3 matrices in SU3, or diagonal matrices, and write down the lines where two eigenvalues are equal, you will find a picture of this sort. And if you take the orbit of any point here, the marvelous thing is that you'll find this orbit is perpendicular to that 2 plane, and it hits it, comes back once in each one of these symmetry places. So the orbit goes out and comes back. So if you study the distance from a general point, let's say, to the orbit, then you easily check that the critical points of their functions are precisely these intersections. So there we found only 2. Here we would find 6. And more than that, if we draw the lines, just as here, you remember we had the minimum when we didn't hit a focal point and the maximum there. Here the number of negative directions at the corresponding critical point is just the number of times you cross these lines. So that means that this thing would be 2. This would be 2. This 4, 4, and 6. So that the Morse series of this adjoint orbit would be 2t squared plus, what am I doing here? 2t plus 2t to the 4th plus t to the 6th. And lo and behold, they were all even. So this is the actual topology of an orbit in SU3. And now this thing here is the, how shall I put it? The marvelous thing is that this happens for all these compact Lie groups. The picture is the same. This is called the Weyl group, of course. This is the Lie. You have to look only at the Cartan subalgebra. You have the Weyl group. The general orbit, adjoint orbit, is actually parameterized by the elements of the Weyl group. And these indices that I've written down geometrically, the algebraists usually like to write down as the number of negative weights that have been changed by an element of the Weyl group. So this was, I think I was the first to notice this. And it was great fun, and it started to make me think, well, maybe we can do the same thing for the loop space of the Lie group. So, and as it turned out, you can indeed. So this is where this picture will come in. This is, unfortunately, the blackboard is too small for me. No, but we have enough room here. Now what is this? You remember I just showed you in SU3, in the Lie algebra, in the matrices of trace 0, 3 by 3 SU3 matrices, the places where 2 eigenvalues were equal. Now you can actually look in the group at the diagonal matrices and draw on the space of diagonal matrices, which is a two-dimensional torus, all the places where 2 eigenvalues are equal. And then you take the universal covering of that, and you get obviously this picture. And this picture has additional information, namely, if this is the origin, then here is the lattice that and so on. So I recover now, on the plane, I recover the picture of this diagram, as it's called, of the Lie group on the maximal torus. And I get a picture of this sort. We get a lattice together with planes called the root planes, but they now form a tessellation of the whole plane. And now the beautiful thing is the geometry comes into the fact that in a Lie group, if you start a geodesic in a general direction at the origin on a torus, it will stay on the torus. So that the only geodesics that join two close by points, which are in general positions, you can actually see them as straight lines on this universal covering. So if you, for instance, if this is the origin, and I'm looking at the space of paths which go from here to here, then here is the first geodesic. But of course here is another one. Just like in that earlier picture of what I was drawing there, you get a very beautiful linear picture of all the geodesics in question. And so you have to then only count, again, try and find the directions of steepest descent. And you find, just as before, as you might conjecture, that if I draw, for instance, this geodesic, I just have to count the number of times it crosses the planes and multiply by 2, and that gives me the number of negative directions. So I have a complete picture of all the geodesics joining two general position points on the Lie group. Now you fiddle a bit about this. There is an obvious, the symmetry group now is larger than before. So I can now do the following thing, that I can try and keep track of this situation more systematically. And this is called a positive chamber in the Lie group industry. So you choose a positive Weyl chamber. And then obviously every geodesic can be rotated into this one by conjugation. So I can take these points which are spread all over and always rotate them back into the fundamental chamber. And the beautiful thing is that I completely fill out this chamber, so that I don't have to draw these cues so carefully anymore. I can indicate them by just, so there's a Q here, there's a Q here, there's a Q here, a Q, so on. So I just, well, the positive Weyl chamber is here. And so if to each one of these, there is a unique geodesic that corresponds to it, and I can read off its index. Now, because the index is given by counting how many lines you cross, let's do that here, for instance. So this is, of course, this is called an alcove in the industry. This alcove represents 0. Here, the Q that was in here, you get to with crossing just one line. So here you put a 2. Here you put a 4, 6, and so on. So for SU3, you see that the Poincare series, and now note it, because they are even, this already actually computes the cohomology. And so the answer is, if you do a little counting here, this line gives you 1 over 1 minus t squared. and this, and then you can repeat this. Once you have added all these together, you can add these lines, and there you notice that you always go up by 4, so it is times 1 minus t to the 4th. And that, of course, is the correct answer. And this way of getting at it proves that there is no torsion in the space path on the Lie group, and that was at the time unexpected because, of course, the Lie groups, the higher Lie groups, do have torsion, but they lose it all in the step to their loop space. I don't know how much time have I got left. So, all right, so this now you can see quite easily how it extends to the classical groups. This sort of information about the Lie group is precisely the sort of information that is used in classifying them, and so it was very easy to write down the corresponding formula. Let's actually, for those of you who don't know, let's compute this way what the loop space of G2 is. You know, G2 is a more sophisticated object, which most people don't know so well, but I know there are some people interested here. I don't know, do you know the Poincare series of loop? Well, if you look at the so-called diagram of G2, it's very easy to obtain it from the one of SU3. I mean, these pictorial methods, of course, only work or last for groups of rank no greater than 2. But G2, thank God, is at rank 2. So all you have to do is add these lines to. I hope I'm. I'm missing a few. Uh-oh. Maybe I have enough now. Here, you see here now the Weyl chamber would be like this. And it's these little, it's these shapes that play the role of the alcoves. And so I start here with 0, 2, 4, 6, 8, and you'll find that the first time I get something else is 10. Here I'll have 2 10s joining. So the loop space of G2 is 1 over 1 minus t squared, 1 minus t to the 10th. And so as far as the homology of the spheres that underlie it, they would look like a 3-sphere cross an 11-sphere. And well, this was great fun for me to find out, because I knew nothing about G2 at all, but the world at that time didn't know anything about the topology of G2. And from this one could immediately decide that, for instance, pi3 was the infinite cyclic, and that the next homotopy group was 11-dimensional. Well, so this is to show you what, as I say, Morse missed. If you had talked to Hermann Weyl just a little bit, right? This is really, it was all completely in his grasp. I mean, he could have done this in a moment's time. But we all, unfortunately, tend to miss these opportunities. At this stage, I could really start a longer lecture. because these diagrams, of course, you should think of them as little what sticks out in an iceberg, because since the period I did this, a tremendous amount of information has been found out about, in particular, about this situation. You notice that this, to me, it already was clear, this looks very similar to my original computation in the Lie algebra situation. And I could never, and here you notice that this loop space seems to be made out of many copies of what I found in the infinitesimal picture. Well, all that has been completely cleared up in the meantime. This marvelous world of the Kac-Moody Lie algebras, their diagrams, their topologies, their representation series. That to me was a very exciting moment when really the whole classical representation theory of the compact groups suddenly was lifted up and extended to the Kac-Moody algebras and the representations of positive energy. These things came as an impetus from physics. And of course, they've had their repercussions in, not just in this context, but in algebraic geometry and even in p-adic theory. But I think that's all I have to say. Thank you.
Thank you, Raoul, for a beautiful talk, and I think we have time for one, perhaps two questions or comments.
I'm always very clear. Oh, no, Mark. That trouble.
Did Morse and Weyl talk at all about other things?
Well, Morse was, in some sense, a sort of, he communicated only outward. I didn't see him palling around with any of the professors very much, but he was a wonderful, although he was domineering in that sense, he was at the same time rather humble and for instance, and very informal. On my 26th birthday, he was invited to a little party we had on the thing, and he immediately challenged me to a race to the nearest tree. But the only people that I saw talking in an easy way to each other were really von Neumann and Hermann Weyl. And really of the permanent members at the time, Hermann Weyl seemed the most at ease here and was a wonderful presence.
Okay, thank you, Raoul, again for a beautiful talk.